Okay, we continue to learn Chapter 4, Linear Transformations. Section 1, Definition and Examples. Part 2, now we learn the image and kernel of the linear transformation. Okay, let L V to W be a linear transformation. The kernel of L, denoted KER, is defined by this way. So kernel of L equals V belongs to the vector space V, such that L function V equals the zero vector in the W space. Okay, so we can see from this figure. So this is a original vector space V. And if you function on L function on this vector space, you will get a set in this new vector space W. And some vectors in V are special. Using L function on these special vectors, they become the zero vector in the W space. So we give this set of vectors as a kernel of L. And now we see the definition of image. Let L V to W be a linear transformation, and let S be a subspace of V. The image of S, denoted L of S, is defined in this way. See, here is L of S equals W, belong to the vector space W, such that W equals LV for some V belongs to S. We see this figure. So we have a subspace S in V, and using L function on the vectors in S, you will get a set of vectors in W. We call it L of S, and L of S is called the image of S with respect to this linear transformation L. Okay. The image of the entire vector space, the whole space V, LV, is called the range of L. So the range of L means you using this operator on every vector of the original vector space, and you will get this L of V. So this is a range of L. We have this theorem. Let L V to W be a linear transformation, and S is a subspace of V. Then, first, the kernel of L is a subspace of the original vector space V. And we also know L of S is a subspace of the image vector space W. Okay. This is a proof. In order to show the kernel of L is a subspace of V, we need to check if alpha V is in the kernel and if V1 plus V2 also in the kernel. Okay. So first note that the zero vector in V belongs to this kernel of L, so this kernel is not empty. And if V belongs to kernel of L and alpha is a scalar, then L function on alpha V equals alpha function on alpha times L function on V. So this comes from the definition of linear transformation. Because LV equals 0W, and by the axioms of vector space, we know alpha times 0W just be 0W. Okay. Therefore, from this relation, we know alpha V belongs to the kernel of L. Okay. And if V1, V2 belongs to kernel of L, then we check L function on V1 plus V2. We want to show that this one also equals 0W, then this vector V1 plus V2 also belongs to kernel of L. And using the definition for linear transformation, L function on V1 plus V2 equals LV1 plus LV2. Equals 0W plus 0W equals 0W. So we show V1, V2 in a kernel of L. Hence, kernel of L is a subspace of V. And now we show the second statement. We want to show LS. The image of S is a subspace of W. Okay. In order to show this, you need to show that for any vector in L of S and any scalar alpha, alpha times this vector also in W. Right? And you also need to show that for any two vectors in L of S, for example, W1, W2, it's a summation also in L of S. Okay, so we see in detail how to show this. Similarly, 0W equals L function on 0V belongs to L of S, so L of S is not empty. Okay, and if W belongs to L of S, then W equals LV for some V belongs to S. This is a definition for L of S. Must be some vector V such that W equals LV, then W in L of S. And for any scalar alpha, we have alpha times W equals alpha times LV. See here, W equals LV. And using the definition for linear transformation, we can put alpha in. So we have it equals L function on alpha V. And we know that alpha V belongs to S. This comes from the definition of a subspace, the closure property of a subspace. So this L alpha V belongs to alpha S. So now we show if W is in alpha S, alpha is any scalar, alpha W also in alpha S. And also for any W1, W2 belongs to alpha S, belong to this image. We can find V1, V2 belong to S such that W1 equals LV1 and W2 equals LV2. This comes from the definition of image of S. And then you know W1 plus W2 equals L function on V1 plus V2 using the definition of linear transformation, which belongs to L of S because V1 plus V2 in S from the subspace of S. Okay, and then we know LS is a subspace of W because it is closed under both scalar multiplication and a vector addition. Now we look at a simple example, example 11. Ask you to find what are the kernel of L and image of R2 for the linear operator L on R2 defined in this way. So L function X, transform X to new vector. This new vector, the first component is just the first component of the original vector X. And here the second component is 0. Okay, in order to find the kernel of L, then we need to find the vectors such that L of X equals 0, 0. Then this means X1 must be 0. So a vector X in kernel of L, if and only if X1 equals 0, thus kernel of L is a one-dimensional subspace of R2 spanned by E2. Okay, and when consider the image of R2, the image of R2 then should be this form, the vector in this form. So it should be X2 equals 0. So it is spanned by E1, also a one-dimensional subspace spanned by E1. Okay, so vector Y in the range of L, if and only if Y is a multiple of E1, thus L of R2 is a one-dimensional subspace of R2 spanned by the first coordinate vector E1. Okay, now we see another example, example 12. What are the kernel of the linear operator L and the image of S where L is defined in this way? So the first component of L of X is X1 plus X2. So you do the summation of the first and second component of the original vector X. And the second component comes from the summation of the second and the third components of the original vector x. Okay, and S, the subspace of R3 spanned by E1 and E3. So in order to find its kernel first, we need to find such x in R3 that have this relation x1 plus x2 equals 0 and x2 plus x3 equals 0. So you can find its a kernel to be in this way. So its relation is like x1 plus x2 equals 0. So we just set x1 equals a, and you'll get x2 equals minus a. And because x2 plus x3 also need to be 0, so you have x3 equals a. So the kernel space is such kind of vector where a can be chosen arbitrarily in real number. Okay, and now consider S, because S is a subspace of R3 spanned by E1 and E3. So spanned by E1 should be like some scalar times 1, 0, 0, right? E3 should be some scalar times 0, 0, 1. So this means the first component and the third component for these vectors in this subspace S can be arbitrarily chosen. However, the second component in this vector in this subspace S should be 0. So its image is just like x1 here and then x3 here. And because this vector is only in R2, so the image of this S can constitute the whole space R2. Okay, so if x belongs to S, then x can be written in this way, equals a, 0, b for some scalar a and b, and L of x equals ab. Therefore, Ls equals R2. Note that the range of L is also R2. Okay, now see this simple example. Example 13. Let D, P3 to P3 be the differentiation operator defined in this way. D function on Px equals the first order derivative of Px. And the kernel of this mapping, the kernel of this operator consists of all polynomials of degree 0, right? Because if here Px is a constant, then you do the first order derivative, it is 0, right? So the kernel of D consists of all polynomials of degree 0, contains all the polynomials that are constant. Thus, the kernel of D equals P1. P1 means the degree of the polynomial function with degree less than 1. So it's a constant, okay, degree 0. And any polynomials in P2 have antiderivatives in P3. Therefore, we know dP3 just equals P2. So this contains all the polynomials of degree less than 2.